A single careless signature at a desk, a stack-up tolerance deviation on the shop floor, or an unmonitored flash of humidity during assembly. In the automotive industry, these are not ordinary production fluctuations. They are the genesis of historical catastrophes. Consider the Takata airbag crisis, the largest recall in automotive history. The root cause? The ammonium nitrate compound inside the inflator capsule shifted phases over time due to environmental moisture and temperature cycles. A micro-imperfection in the sealing ring transformed a driver safety mechanism into a lethal shrapnel bomb. Why did hundreds of engineers fail to foresee this critical failure mode effect? Because they treated risk analysis as a static, checklist compliance document to be pulled from a folder on audit day, rather than a proactive engineering discipline. Today, our objective is not paper-pushing bureaucracy. It is to master the risk engineering required by global automotive titans like Ford, General Motors, Stellantis, and Volkswagen. Let us break down the new paradigm of AIAG-VDA Harmonized FMEA. The global laws of risk management were forged through raw operational necessity. The roots of failure mode and effects analysis, FMEA, trace back to 1949 with the deployment of the military standard MIL-P-1629 by the U.S. Armed Forces. This uncompromising aerospace and defense discipline reached a critical evolutionary milestone during NASA's Gemini and Apollo programs in the 1960s. The mandate was absolute. Execute single-point failure analysis across multi-million-dollar mechatronic systems to eliminate catastrophic risks before launch. When Ford Motor Company integrated this methodology into the automotive sector in the late 1970s, it became the structural backbone of component-level risk management for high-volume mass production. However, the automotive ecosystem eventually fractured into two distinct methodological camps. The North American ecosystem, governed by the Automotive Industry Action Group, AIAG, prioritized a form-driven, row-by-row spreadsheet compliance approach. Conversely, the German Automotive Industry Association, VDA, developed a systemic risk philosophy rooted in structural block trees and functional networks. This deep philosophical divide forced global suppliers shipping components across both continents to manage highly inefficient, duplicate documentation. The exact same component required separate risk profiles to satisfy different regional OEMs. Published in June 2019, the Harmonized AIAG-VDA FMEA Handbook was engineered to dissolve this operational gridlock and establish a unified global engineering vocabulary. With this harmonization, FMEA completely ceased to be a static Excel spreadsheet filled out by a lone engineer. It evolved into an interconnected, hierarchical database architecture. The new rule of the industry is clear. Form-driven analysis is dead. Modern risk management must be structure-driven. If your structure, function, and failure trees are not mathematically locked together in your database, your work will be flagged as a major non-conformity during international audits. In engineering management, the most critical error is confusing which risk belongs at which table. The IATF standard separates supplier responsibilities with a razor-sharp line. If you define the geometry, material characteristics, and tolerances of the product, you own the design responsibility. Consequently, you are legally mandated to execute a design FMEA. Your ultimate objective here is to prevent failure modes triggered by design choices. However, if the customer hands you a finalized technical drawing and says, "Just manufacture this exactly as written," your scope is build to print. Your responsibility shifts entirely to the process FMEA domain, covering everything from incoming material control to final dispatch. Here, the focus is never component geometry. It is managing the variation generated by the 4M framework: man, machine, material, and method. Do these two traditional FMEA types suffice when complex mechatronic architectures, like autonomous driving systems, radar sensor arrays, or intelligent braking modules, take control of modern vehicles? Absolutely not. This is precisely why the 2019 Harmonization introduced an entirely new module, Supplemental FMEA for Monitoring and System Response, known as FMEA-MSR. FMEA-MSR begins where conventional detection controls end. This module analyzes how a system electronically and software diagnostically captures a physical failure while the vehicle is actively operating on the road. When engineering an FMEA-MSR, we are legally bound to ensure absolute alignment with ISO 26262 functional safety standards. Can the system immediately generate diagnostic trouble codes, DTC, upon failure detection to alert the driver via the cluster display? More importantly, can the system execute a software loop to command a safe state mod within milliseconds to protect the vehicle occupants? The answers to these diagnostic questions directly dictate your project's ASIL, Automotive Safety Integrity Level, rating. Let us test your field judgment with a real-world forensic scenario. You are investigating a sensor drift failure within an electronic throttle body. If the root cause is structural wear on the assembly fixture of the production line, it belongs in the PFMEA. If the cause is a diagnostic monitoring loop error within the sensor's embedded software, it belongs in the FMEA-MSR. If the cause is stress concentration due to a sharp radius geometry on the housing casting, it belongs in the DFMEA. Log this under the wrong FMEA type, and you will misallocate and waste your entire engineering validation budget. The defining failure of traditional FMEA sessions was watching engineering teams lose themselves in row-by-row data entry without analyzing the actual system architecture. The 7-step approach of the AIAG-VDA harmonized methodology completely structurally dismantles this bureaucratic burden. The core engine of this framework is the strict vertical integration of structure analysis, function analysis, and failure analysis. When constructing your failure tree, you must rigidly execute this logical hierarchic: failure effect, failure mode, and failure cause. Always remember, the failure effect is derived directly from the failure mode, and the failure mode is the physical manifestation of the underlying failure cause. For years, the automotive industry made one major mistake in risk assessment, relying too much on RPN, the risk priority number. Multiplying severity, occurrence, and detection blindly creates a misleading mathematical score, not a clear picture of the actual risk. The new handbook ended this numbers game and replaced it with action priority, or AP. Instead of focusing on a multiplied total, the AP system classifies risks as high, medium, or low by giving direct weight to severity. If a design or process risk can affect human safety, the severity score is automatically 9 or 10. In that case, even when occurrence is very low and detection controls are strong, the action priority still becomes high. In other words, the algorithm gives a clear message to the engineer. You cannot ignore this line. This risk requires an immediate technical action. Consider this proactive field scenario. You are managing a critical manufacturing line with a process step flagged as AP high. Due to severe budget constraints, you cannot invest in a new vision camera system for downstream detection. To legally and structurally reduce the action priority level, do you execute a geometric design modification, a Poka Yoke feature, that physically prevents the incorrect assembly at the source? Or do you accept the current process state and trigger an executive risk sign-off protocol? The answer is absolute. You must execute the geometric design change. By making incorrect assembly physically impossible, you structurally reduce the occurrence score of the failure cause to 1. In the AP matrix, even with a severity of 10, an occurrence of 1 automatically drops the action priority down to low. You eliminate the need for $1 million camera, optimize capital expenditure, and achieve bulletproof compliance for your next IATF audit. Bypassing this with an executive sign-off protocol does not mitigate the real risk. It simply documents corporate liability. A design change is not just an elegant engineering preference. It is a normative mandate. In the global automotive supply chain, FMEA is not a static document to be filed away. It is a live, regulatory contract. Let us look directly at the reality of IATF 16949, Clause 10.2, Nonconformity and Corrective Action. You receive a critical field claim or a 0-kilometer defect alert from an OEM customer. Your quality organization immediately deploys an 8D forensic investigation. The single most expensive mistake made in automotive quality is signing off on the 8D corrective actions, sending it to the customer, and leaving the case file dead on a server. The IATF standard explicitly dictates the technical root causes uncovered during your 8D path must be directly injected back into your living design and process FME as to reevaluate systemic risk across the plant. until your FMEA database captures those lessons learned. That corrective action is legally incomplete. The vertical integration continues deeper. Under Clause 4.4.1.2 for product safety, any FMEA line displaying a severity score of 9 or 10 automatically triggers a critical characteristic (CC) designation. This is where the German process audit standard VDA 6.3 exerts its full force. VDA 6.3, starred questions P4.2 and P6.2.3 audit the absolute vertical pedigree of these safety symbols. If a safety characteristic defined by AIAG-VDA on the drawing does not flow seamlessly into your process FMEA, copy identically into your process control plan, and link directly to the specific inspection step on the operator's standard operation sheet, SOS, at the station, the auditor will issue a direct 0 score for that starred item. No matter how clean your factory floor looks, a 0 on a starred question automatically drops your audit rating to a C, meaning you fail the audit and lose your approved supplier status. Beyond the baseline standards sit the customer-specific requirements, the CSR barriers dictated by individual automotive groups. Ford's CSR mandates that before you even input data into your FMEA rows, you must finalize and attach a verified boundary diagram and a parameter diagram to lock in system robustness. Furthermore, Ford expects a software-linked connection between your master foundation FMEA library and your part-specific variants. General Motors deploys an even more aggressive operational rule, reverse FMEA. GM requires your cross-functional engineering teams to physically walk the manufacturing lines at regular intervals, intentionally bypass process steps, executing controlled fault injections, and physically verify whether your documented Poka yokes and detection mechanisms actually intercept the defect on the line. GM explicitly bans arbitrary RPN limits. Your risk prioritization must live exclusively within the harmonized AP tables. Meanwhile, Stellantis enforces unique action priority adaptations, requiring all safety-critical parameters to maintain a severity score of 10 with no compromise. Let us establish a clear operational rule. When is an engineer legally mandated to pull an FMEA file from the database and execute a revision? There are 4 non-negotiable triggers. 1. Whenever an engineering change notice, ECN, modifies the product design or process parameters. 2. The moment a field failure or customer complaint is logged. 3. When an internal or external audit identifies a system deficiency. And 4. Even if your production metrics are completely stable and 0 changes occur, your cross-functional team must review your master FMEA documents at least once a year to maintain corporate memory and process protection. As an FMEA facilitator or moderator, you must recognize the single root cause behind failed, chaotic risk analysis sessions, trying to build your risk architecture during the actual meeting. A highly successful FMEA is won or lost before the team ever enters the room. You must deploy the AIAG-VDA 5T framework to freeze your intent, timing, team structure, tasks, and tools beforehand. If you are facilitating a process FMEA, your baseline package must contain a process flow diagram that perfectly maps every single operational sequence, aligned 100% with your SAP routing steps. Your analysis boundaries cannot be limited to simple assembly steps. Your scope must systematically track every step from incoming material receiving dock through internal logistics and storage up to final container loading for dispatch. For a design FMEA, your technical entry gate requires a verified boundary diagram and an interface matrix. Your boundary diagram defines the exact physical and functional limits of your engineering ownership. Your interface matrix must mathematically score how neighboring subsystems interact, grading connections from a +2 positive interaction down to a -2 harmful interference across physical, thermal, or electrical vectors. This leads directly to your ultimate diagnostic weapon, the parameter diagram, or P diagram. Your P diagram charts the 5 inescapable real-world noise factors that want to destroy your product's performance: piece-to-piece manufacturing variability, material degradation over time and mileage, unpredictable customer driving profiles, global climate extremes, and neighbor system interactions. If you try to write failure causes without mapping these 5 noise variables first, your FMEA rows will be nothing but wild guesswork. Risk engineering requires a highly specialized team. Your cross-functional team must actively unite design, quality, production, methods, and maintenance engineers. The rule here is uncompromising. Any team member who has not been verified in baseline FMEA taxonomy cannot contribute effectively to the analysis. As an FMEA moderator, you hold absolute process authority. If your core engineering team fails to show up, or if your required pre-session technical package is incomplete, you must cancel and postpone the session immediately. You do not waste engineering hours trying to review risk architecture with missing data. When the session goes live, you do not allow an unstructured brainstorming session to hijack the agenda. Brainstorming goes through the roof, and your cognitive load skyrockets, destroys retention curves, and results in a disorganized document. You must execute the rigid, data-grounded 7-step approach. This structured hierarchy automatically silences unbacked opinions and guides the team to focus purely on actual CPK variation trends, process capability limits, and documented material data. Eliminate the old excuse of operator error from your vocabulary. When a torque wrench clicks out short or a component is misaligned, typing operator carelessness into your failure cause column is an engineering failure. Operator error is a symptom of a weak process architecture, never the root cause. Challenge your cross-functional team through the 4M matrix. Why did the fixture geometry allow the orientation error? Why did the tool control loop fail to intercept the short torque? The moment you stop blaming the human operator, you begin engineering systemic reliability. Once your FMEA session is signed off, its parameters must instantly leave the digital server and embed themselves directly into the shop floor. Every single detection control you write in your FMEA columns must map identically onto your process control plan, with exact sample sizes and frequencies, and convert directly into the operator's daily standard operation sheet, SOS. If an auditor tracks a critical process step on the line, asks the operator how that parameter is verified, and the operator's localized workspace instruction does not match your FMEA master sheet, your quality control architecture collapses. FMEA is not a filing cabinet document. It is the real-time operational heartbeat of your manufacturing plant. When you close the loop between your engineering data arrays and your field reality, your 8D analyses stop functioning as firefighting damage control and transform into permanent preventive assets. You stop reinventing the wheel with every new product launch because your Live Foundation FMEA database automatically delivers a 70% reduction across your engineering launch cycles, preserving decades of manufacturing wisdom. FMEA is not a bureaucratic burden. It is your ultimate strategy for manufacturing survival. Stop treating it as a dead piece of paper. Take the smallest process nonconformity logged on your shop floor tomorrow morning, map it directly back to its vertical FMEA row, and activate your engineering data network. I am Halil Ibrahim. Until our next forensic engineering analysis, stay data grounded, guard your process capabilities, and stay safe.